Okay, so today we're going to start the last one of Maxwell's equations. It's called Faraday's law, and most of the really practical things you get with magnetism actually come from this law. Okay, so we'll find out how this works. All we're going to do is a lot of qualitative stuff for a while before we actually figure out how to do it analytically. So because the qualitative stuff is a little on the advanced side. Okay, so we're going to get Faraday's law. And this is the last four. So how does that work? Let me give you what the idea is here, then I'll explain what it is. What we're going to find out is that Faraday's law states that a changing magnetic flux creates an electric field. That's what the law is going to actually state. And what I want to do is actually show you how this actually works. So generators. No. Yeah, generators will actually work like this. Okay. Just out of curiosity, this is actually this is interesting. This would have actually been called Henry's law. There was an American physicist at the time who lived at the time of Faraday. His name was Joseph Henry, who actually discovered this law before Faraday. And he knew that he had discovered something actually really important. And so he basically kept on checking and checking and checking and checking his results because he knew that this was going to be a groundbreaking law. At the time, American science was considered very practical. You know, we had steam engines and stuff like this, locomotives. And that was always, if you want to insult a physicist, you refer to the work as being practical. And he realized that this was a major theoretical breakthrough. And so he kept on checking his result. And then Faraday came along, basically did a couple of experiments and said, oh, this is a law, and published it immediately. So Henry thought he was ahead of the Europeans, and he was, but he was only ahead by several months. He wasn't ahead by as much as he thought. And so Faraday got the credit for it. And a lot of the American scientists, physicists got upset with Joseph Henry for basically taking so long to come up with the law because he knew what it would have done for American science. And so they were treated him fairly badly. And then people realized they really screwed up and treated him badly. And then they eventually named a unit after him. So later on, they're going to get something called a Henry. And it's named after Joseph Henry. So just kind of interesting thing. Okay, so what is this law here? I'm going to give you a thought experiment. Let me give you the law first. Okay, so here's the law. We're going to have the script D here. Okay. This script D is called an EMF. Okay. What does EMF stand for? You probably know. Electromotive force. Okay. Electromotive force. It acts just like a voltage difference. Okay, it's not a voltage difference. It's actually, but it's going to look almost mathematically identical to it. So you call it an EMF here. So this is going to, for all practical purposes, this acts like a voltage difference. Let's make sure that's still in focus here. And it is. Okay. And we're going to find out that this right here is going to be this E dot DL. Okay. I'm not developing any of this yet. I'm going to kind of show you where this comes from. Okay. Qualitatively. So your electromotive force is going to be this guy here. And this is going to equal minus dPb dt, where phi b is the magnetic flux through, and this is the difference here, through a closed loop, not a closed surface.
Makes sense because we have a line.
Correct. So this guy here, by closed surface, what do I mean by that? I mean this. Okay, so let's say I have a loop here like this. Here's a loop. Here's a loop. And let's say I have a magnetic field coming out through here like this. Okay, if I had a magnetic field coming out through here like this, let's say this is a magnetic flux, a magnetic field. If I basically look at the magnetic flux through the surface here, that's what this magnetic flux is here. It's not a closed surface. What's a closed surface?
Something, it's a surface
This is a closed surface.
on which you can go any direction to reach any point. I was trying to like get a mathematical definition of it.
It's this.
Yeah.
You're looking up in a math dictionary. So picture me holding this. So if you have a magnetic field going through here like that, that would be a closed surface. And what do we know about this magnetic flux, guys? What do you know about this magnetic flux through a closed surface from yesterday?
0.
Wednesday?
0.
It was 0. Okay. So that's what we have here. So we have another way to produce a magnetic field here, or an electric field. So if you take a magnetic field here, let me put this down here. So this magnetic flux, this guy here. Again, this is only through a closed loop, not a closed surface here. If you have a magnetic field here that's changing with time, that's going to produce an electric field. Okay. What's the other way to produce an electric field?
Charge.
You don't even have to move a charge. Just if you have a charge there sitting in your hand, you have an electric field.
How?
Okay.
Okay, so a magnetic field is produced by accelerated charge.
By a moving charge,
By
not
okay,
accelerated.
moving charge. So if we have a magnetic field, even like a constant magnetic field, there's a
Yep.
moving charge, which already has an electric field.
Yep.
How does that, like, doesn't it,
I can't wait to find out. Okay, I take good notes. I've always wanted to know how that works.
I mean, don't you see the contradiction? You don't have to.
I sure do. I can't wait to find out what the answer is.
Okay.
Okay, take good notes. I hope it makes sense. Okay.
I will.
It hasn't yet, but I'm certain it will soon. Okay, so let me give you the thought about the ideas behind here. Let me kind of qualitatively list up this up. So this will be a thought experiment. So consider. Thought experiment. Thought experiment is one of the few German words I know. Okay, it's Gedanken experiment. So if anyone says, well, consider the following Gedanken experiment. Okay, Gedanken is just German for thought. But if you say thought experiment, it doesn't sound sophisticated. So you put thought in either Latin or you put it in German, and German wins out. So you say, consider the following Gedanken experiment. People think you're smart. Look how far I got. So let's go through and see this. So let's say we have a little magnet here like this. Here's the North Pole, here's the South Pole. How does a magnetic field look for this? It comes out like this. Not like that. Right, and you have more lines like this. Okay. Now I'm going to have a little loop here. Here's a little loop. Actually, there's a little loop. Wouldn't be a toroid. Well, you could call it a toroid, but until you wrap wire out.
But wouldn't it have a, wouldn't that be a closed?
I can't wait to find out what it's going to be. Okay. So here's a little loop, and I'm going to take that loop and I'm going to move it this way like this. Okay. So I have a magnet here. Let's say here's my magnet. North Pole, South Pole, and I have a loop. I'm going to take this loop and I'm going to take this loop and I'm going to move it toward the magnet like this. That's all I'm going to do. Okay. What would happen to my little, and this is some metal loop here. What would happen then? Let's consider the following. Let's say you're a tiny little positive charge sitting here by your lonesome. Okay. Right, because metals have basically moving charge. We assume that the positive charges move. So we're going to look at that one here. I'll look at this one here as well. So what would happen to you?
There's a force.
Going what direction? I'm hearing away.
You're moving, it's V.
Why would there be a force on that low charge?
V cross V.
Yeah, we know that the force.
Oh, charge due to magnetic field is V cross V. So it's moving down.
So we would have this force. It's QV cross V. So what's the V for my little charge here?
For what?
The V. The V is like that.
Down.
That's my V.
And
The V is going off like that. So what's the force in that? Right and roll
into the board.
into the board. Everyone agree? How's your right hand rule work?
Put your fingers in the direction of the first one
Fingers direction first.
and curl them into the second
Yeah,
one.
bend them into the second. So let's do this. V is down. V is like that. My force is, there's a force going in here like that. So the force is going on this way. Here. What about my little friend over here? This is V. And V is like, okay. It's a little more. How's that one go? V crossing V, that one's coming out. I can do this for all the things here. What's going to happen to all the forces on those little positive charges? Yeah, they're going to. It's actually going to make a current going this way because you're pushing the charges here, pulling them here. You can go all the way around this whole ring and you get something similar. You're basically going to get a current going like this. So you're going to get an induced current. This right here is your induced current. That's what you're getting. Okay, now here's where the thought experiment comes in here. Let's imagine instead you actually happen to live on this ring here. So consider the same event, but point of view. Someone sitting on the ring. Let's show that picture. Here's the little ring. Here you are, like this. Okay. And from your point of view, you don't think you're moving. What do you see instead happens?
What?
From your point of view, you're just on the ring here and life is good. What do you see happen?
You're moving down.
No, you're moving with the ring. You don't see yourself moving.
Oh, yeah.
You're going to see
There's charge moving
going in what direction?
towards you.
Up toward you. So from your point of view, this magnet is going up from here. So from the point of view of the observer on the ring, the bar magnet is moving toward you. That's so fat. Okay. But will this person have this equation here? No, right? There's no charge moving here. Okay. But instead, what happens? Well, you have this B field coming out like this. Okay. What would this person say? Well, this person would say, well, wait, as this magnet's coming up like this, what's happening to the magnetic field going through here?
It's getting stronger.
It's changing with time.
Yeah.
So this person is going to see this magnetic field going through this loop here changing with time.
Yeah.
And this person is going to have to say, I'm getting a current still going like that. The current still stays the same, right? The current never goes away here.
It doesn't matter what way.
Yeah, that's an actual physical thing. If you're getting a current going like this, you can't go to a frame and get that current to that. At least in this case here.
I mean, you can't go around in circles.
Okay. So the observer here, the observer still sees a current. Okay, and they also see the change in magnetic field here. So what would this person have to do? This person would have to, you'd be forced to, this would be an empirical result. You'd be forced to conclude that if you have a magnetic field here changing with time, okay, if you're getting a current, what must this changing magnetic field do with time? How do you get a current to move? An electric field. So this person would be forced to conclude that basically by having this magnetic field change with time here, I'm somehow creating an electric field. And that electric field is responsible for this current. Okay. Make sense?
Where do we get the equation for force?
This equation for force is when you have a charge moving a magnetic field.
Yeah, but like how do you get that?
In this course, you don't. I give it to you. I say it's empirical. If you want to see it fundamentally, where it comes from is from spectral relativity.
So it doesn't depend on an electric field being considered there. in the beginning.
No, in this case here, there isn't all that. Well, you would have, in this case here, you wouldn't have, you'd have a charge moving through a magnetic field. And it turns out that gets a little more complicated in that case, because when you're working out with special relativity, it's entirely to go with transferring from frames. So you have one frame here where I'm stationary. I'm seeing a charge moving like this. But if I'm moving actually with that particle, I'm not going to see, I'm going to see this particle stationary. And when you actually set that up formally,
Okay, so
but that's
there's
something
no,
well beyond this.
so there's no idea of like, there's no circular conclusion in that. So this,
No.
okay, got it. I'm just trying to see.
No, that's fine. It's not one of it. This is kind of neat stuff. Okay, that makes sense?
Yeah.
Okay. So let's state what this is here. So the observer on the loop would be forced to conclude that the changing D field through the loop is creating an electric field that causes induced current.
So is there like a formula that relates, well, since the magnetic field and the electric field have to be somewhat.
They are connected, and it
Yeah,
comes
but
through
like, how
Maxwell's
would you-
equations.
Yeah, but like, is there like one formula that conveys, like, if you have set, if you're doing this with an electric field, here's the, what, the magnetic field that.
Well, Maxwell's equations will do that. And there's a more, once you take a really complicated view of Maxwell's equations, you can actually reduce them to actually two. That's elegant. And you'll see that in your algebra. Just to let you see, you're gonna eventually get something that looks like this. That's what you conclude, but you don't know that yet.
It just.
But when you do, you're gonna look at that and say, whoa, this is a response. Okay, so let's kind of state what this means here. So the result of this plot experiment is Faraday's law. This is not a proof. I cannot prove Faraday's law at this stage here. I'm just stating it as a fact. Okay, saying if you do this here, you can conclude this, and then you actually then end up with Faraday's law. I can't prove it at this stage here because it turns out the proof is actually, you don't have the mathematics for it. Okay. So let's, I'm going to state Faraday's law here. So this I'm treating as an empirical law. This is an empirical law. Okay. At this quantity right here, this is called your EMF. I'm going to use a script E for this, and it acts just like a volt. Okay. So what this is stating is that if you have basically a magnetic flux that changes with time, you get an electric field. Okay. Which basically this is going to be like a voltage here.
And a voltage is an amount
Well,
of-
now I want to state what the distinction here.
Okay.
Okay, so I want to state the distinction between basically an EMF and a voltage difference, because there's a very important difference here. Okay, this point here is a very fine point. Frequently, this is not done in this course, but I'm actually confident that you guys can understand it. Okay, so here's a very fine distinction. So this is a fine point. So I'm not going to hold you responsible for this. Don't worry about it. But I do want to at least in your head someplace. Okay. What is the difference between an EMF script E, which acts just like a voltage, and an actual. Difference. So I'm going to say that the script D here is acting just like a delta V here. So for all practical purposes, if you have a script D, you have a voltage difference. Okay, but there's a very, very subtle difference here. Let me get this point off, and then all I'm going to do today, so let me explain this dumb minus sign. That dumb minus sign is a completely fake minus sign. Okay, it's called Lenz's law, and it's really quite important. So I want to do today, and probably on Monday, is explain this minus sign after I get to this point. Okay. So let's consider voltage difference. So recall for definition. Of delta. So we have this electric field like this. And I have this point here initial, I have this point here final, and you tell me how we formally define the voltage difference.
It's the energy required to move charge from initial to final path.
Okay, so we said formally. We had some path connecting these two spots here. Okay. And we said that the voltage difference is by definition the change in this U, and this U is the
Conservative energy. Potential or potential energy. Yeah.
for the electric field. So this is your electric potential energy over charge at you. Okay, so we did something else here too. We said if we have electric potential energy, so recall, if you have potential energy, what do we know about that? What is potential connected with potential energy? Only with
Position.
okay, it's only a function of position, but it also only depends on a fine point from 125.
Oh, just like the displacement.
What are the two types of work we have?
Conservative.
Conservative work
And non-conservative.
and non-conservative work. Okay, what is conservative work? It's work that is
Path and-
independent of the path.
Yeah.
And conservative work is path dependent. So recall, if you have potential energy, you are dealing with a conservative force. Conservative forces do path independent. So if I want the work done by conservative force, what is that going to be? That's going to be my F dot DL integral from some initial to final spot here.
Basically a line integral.
That'd be a line. That makes sense? Everyone happy with that? Because if I have a little object here, here's my friend F. Here's my initial spot like this. This is my friend there, F. Okay, how do I calculate the work? I move this over a tiny little distance here. I call that DL. If I want the tiny work to move this object some little tiny DL, that's my F dot DL. And if I want the total work, what do you have to do? You have to sum up all those little contributions along here and you get this right here. So your total work, this guy. Now, if this is conservative, what do we know about going from here to here? It doesn't depend on the path, so I could just as well take this path here.
Just a straight line. You're living on the edge again, right?
You could take that path as that, and you'd get the exact same value, right? Or you could take from this path over here. That one, and you still get the same work. And all we're going to do for the rest of the semester is I'm going to draw multiple paths, okay, for the rest of the semester, and then conclude they're all the same, okay. And then the final will basically be things not related to what we're talking.
It seems like that.
Now, but there's an implication to this. What's the implication of this? How can I then construct potential energy? I say that there's a function called potential energy U that only depends on position. And how can I formally construct path independent work?
It's the potential energy at the endpoint minus potential energy at the beginning.
Exactly. It's the conservative work is by definition change in U, and I put up this word minus on it. Okay. And what is this going to be? This is going to be minus. This change here is going to be U at the final position, x final, minus U at some x initial. Okay. What does this guarantee? This only depends on where I start and where I finish. That guarantees I have path independent work.
Yeah.
That makes sense? So this basically, this weird definition, this guarantees. Uh-oh.
R. A.
Hmm?
Yeah, A.
Hmm?
And I think.
Yeah.
I think it's an
Guarantees. Okay, path independent work. Okay, yes, I realize it's sad that an American is getting basically spelling information from a Russian. Yeah, I know that's sad, but that's just the state it is. Okay, that's okay. So guarantees path independent work.
I'm not watching.
So what do we have here? I can conclude that this work here, which is this guy here. So what do we do here? We take this and we put everything back together. So if I have my change in voltage is in this guy here. I take my friend delta U and I put it in here, and this gives me this minus integral initial. Okay. Now, what do we know about F in this case?
QE.
Is our friend QE. As we confuse with Dewey. So it rhymes. That's important. And that's my voltage difference. And that would be basically when you're dealing with conservative force. So this E here, this is a conservative.
Now it makes total sense why like electric field is the gradient of voltage. Because it's its potential function.
Exactly.
Wow. Calc 3 really helps.
Oh, help more. Okay. Questions with that? Okay. Now we can do more. So let's say here's my initial spot, here's my final spot. I'm going to call this path 1. I'm going to call this path 2. I know that the work done along path 1 has to equal this F dot dl. This is initial final. This is going to be along path 1. The work done along path 2 has to be this initial to final along path 2. F dot dl. If I'm dealing with conservative work, what can I conclude?
They're equal to each other.
They have to be equal to each other. So if F is conservative, okay, I can conclude this guy here. Let's do something crazy. I'm going to take this to the other side. Now, think back to Calc 1. What can you do with those crazy limits from Calc 1? You can flip these and then make this a minus. Okay, so make this a minus, and then plus. So this I can write it as
like connect them.
Yep. One, this is all path 2. This is now final to initial. graphically, what is this telling you? Here I'm going from where to where?
From point initial.
I'm going from 1 to 2. So this right here is this integral here.
Well, it means that you did no work going around.
Correct. Now, what is this integral over here? I'm going from final to initial. So here I'm going back this way like this. So this is this guy here. What does it have to equal then?
0.
0. But hey, if I do this, what am I actually doing? I'm going around a loop.
Closed.
So I can write this as, what's my fancy way for going around a loop?
Loopy thing.
Loopy thing. Okay. And I know that this is my friend QE for this, for the electrostatic field. So this gives me this guy here. This is for a conservative. When we have this, we say we have a voltage
You
difference.
just divided by Q. Right there.
I took the cube over to the other side and got rid of it. Okay. Now, if you look then at Faraday's law,
I mean, that makes sense. That's just,
so if you look at Faraday's law, we have this guy here. So first of all, what does this kind of look like? This EDL, that looks like a voltage difference.
yeah.
Okay, so this looks like delta V.
Oh no, that should be a 0.
Yeah, that should be 0. Okay, but that this kind of combination looks like a voltage difference.
Yeah.
But this does not equal 0 anymore. This equals minus dQdt. What does it mean about this electric field here? It is a non-conservative field. Okay, this is a different element. This is in a different part of the zip. Okay, this is a non-conservative. This is a non-conservative. The C over here is conservative field. So when you have electric fields produced by charge distributions, you have conservative field. How do you get this one here? You have a magnetic field that's changing with time. So if you have a magnetic field changing with time, you are producing an E field here.
That is not.
Okay,
conservative.
but it's no longer conservative.
Wow.
Okay, that's a very, very fine distinction. And that's why you don't call this a voltage difference, you call it an EMF. It's not produced by conservative E field. So that's actually why you call this discrete. A very, very fine point. Okay, a lot of books don't go through this. A lot of professors just bother with algebra. I think you guys can handle it. I'm not going to ask you anything like that.
That's cool.
Okay, I just want you to know it. Yeah. That drove me nuts as a student because when I was a freshman, because I had no clue why we're. It's like a voltage, but it's not, and we're using the same thing, but it's different. Huh? I had no clue what was going on. Okay, questions. Now, what I want to do for the rest of today and probably all of Monday is I want to talk about that dumb minus sign. And then we're going to get a lot of dog and pony show stuff. So we're going to get a lot of demonstrations. Okay, so what I want to talk about is lenses of law. Okay, so you write this, I'm just going to write it as script. When I say the script, this right here, this minus sign right here, this is a fake minus sign called lenses law. It's actually really important. This is going to tell us basically the direction of the induced current. Okay, Lenz's law. Here's the direction of the induced current. Well, I'm not going to tell you why Lenz's law works yet. I'll explain why it works. Okay, I'll tell you right now. The Lenz's law is entirely the result of conservation of energy. That's why you have the minus sign there. But what I do is show you how this works. Okay. and just state that this, I'm gonna write something down that's gonna make no sense. I'm gonna do a whole bunch of examples the rest of the day and all in one day, just giving you qualitative examples of why this works. Okay. Lenz's law states that the induced current will be set up in such a manner, such a way as to oppose, that's the important word, to oppose the changing magnetic flux.
That basically says we gotta put a minus sign in there.
Yeah, and this is, I want to set this up. And let me just give you a couple concepts of what we're going to find for this. This can give rise to really, really bizarre things.
I think it's blurry.
Is blurry again? Yes. Lenz's law is going to give rise to a really, really bizarre phenomenon. Give rise to this. This right here is the pole faces of a magnet here, neodymium magnet, quite powerful magnet. But put these together like this. Now if I do an experiment like this, that's called gravity. See that you couldn't do that without a magnetic field. Okay, that's Lenz's law. But we can now do something like this. I can take this. Okay, I can drop this through like that. Just make noises too. See? Okay, so I'm going to take this, I'm going to pass it around, take this and move it through here like this. You're going to see you can touch it if you want. But you're going to actually, there's going to be a huge drag on this thing. Okay, it's actually quite noticeable. So I'm going to pass this around. You can go like this and go, ooh, this is cool. Okay. You're going to understand how this works. But that's going to be, this is Lenz's law. This gives rise to magnetic braking. Okay, so let's see how this works. It's actually a very noticeable drag. That is cool. Okay, so we're getting, probably on Monday we'll get how that works. Okay.
Oh, so it opposes it because that's what makes the dragging.
There's more to it than that. Okay, so let's go back to this case here. Let's go back to our ring. Let's say here's like this. Okay. Okay, so what will you, when you do these things here, always look at how the magnetic flux is changing. So here's your magnet. So remember what magnetic flux is. How do you define magnetic flux again?
Integral, double
integral
through the surface. B dot dA.
Okay, so what would it be here? If I wanted this right here, I would have some B here like this. This would be my B. How would my dA vector go to the spot? Here's my loop. Notice if you just have a flat surface, it's ambiguous. I can have a dA like this or a dA like that. So that's flat. I'm just going to take it to the bottom. That's going to be my dA. So I take this B dot dA and I'd sum them up over that whole region.
What?
Okay.
Why does your dA go like that?
Because let's say here's my. So let's say here's my loop.
Yeah.
I love performance. See, as a society, we think of ourselves as basically enclosed in some circle of metaphysical reality, but the ontological nature is actually disconnected from basically our metaphysical self. And although we actually might pierce through basically the veil that actually separates basically our ontological nature from basically the stratified nature of society, it's really not. Because you can see that if we're a magnetic field like this, okay, our dA vector it's not aligned. And what my art tries to show is that although we're kind of polarized like this, what we really are is actually more like this. And that's what my art shows. Okay, no, okay, so this is my loop. Here's my dA vector. This is my B vector. How would my dA vector go?
Should it be outwards to the loop?
This could be outward. It's just flat, so there's no outward.
So, but if the loop is like a kind of like a.
This is my surface. This is my surface. I can be outward like this. I can be outward like that. This.
So you're saying that the loop is two-dimensional,
Correct. This is not a closed surface anymore,
but you're drawing it as a three-dimensional one.
because this is three-dimensional. This is the loop here of the circle.
The inner loop of this. Oh, okay,
Yeah.
of the total.
Okay. Yep. So here's my B. Okay, so here's my loop. This is my B. The dA vector would go like that.
Yeah. Okay.
That makes sense?
Yeah.
And then you add them all up here. Now let's ask, how is that changing over time? So if I take that and move it toward here like this, is my magnetic flux increasing or decreasing? What's happening to my B if I get closer to that bar magnet?
That's right.
It's increasing. So as this comes in here like this, the B from the bar magnet increases as the bar magnet gets closer. So the flux increases. So phi increases in the upward direction.
I mean, it's probably. Would it be better to say that the magnetic field is more dense and more upwards at the North Pole, so like it
Yeah,
becomes
it's
more
just, it's
upwards?
just increasing. As you get here, you're getting both effects.
I mean, it
The
could
B
be,
is actually getting actually stronger.
yeah,
And then also you would be getting, as you said, that effect.
but what I'm
The
saying
flux
is
is
that
increasing.
this, like the red is not necessarily a consequence of the blue, because it may be increasing if we didn't have that shade. It could have been increasing to the outside, then flux would be decreasing, but it's specifically.
No, because when you go when you actually do the whole thing here, the actual flux is going to be increasing.
What if it's more dense but flattening out? That means. the
I mean,
flux-
you can, but in this case right here.
Yeah, that's
the
what
flux is
I'm
gonna
saying.
increase.
So because it's not flattening
In
out.
this
it's
case,
straightening out.
here, it's increasing.
Okay.
So what does Lenz's state? This is going to induce a current, but how's it going to induce a current?
Opposite
To oppose the increasing flux, or to oppose the changing flux. So what's the change in flux? The change in flux is that it's increasing in this direction. Does that make sense? So how do you oppose the flux increasing in this direction here? You're going to create another magnetic field going in the opposite direction here. So we need a red one. Okay. So this one here is going to produce a magnetic field going like this. So this right here, this is the induced B field of the loop opposing the increasing flux of the bar magnet. Okay. So to get a current going, how would you then have to have induced current? Think back to your right-hand rule. If I know that the magnetic field is like that, use one of your right-hand rules in reverse to give me the direction of the induced current.
like that.
Oh, okay, well, which one?
So we need.
Okay,
We need to.
if we have current going like this, how do I find the direction of the magnetic field? You wrap your hand in the direction the
Yeah.
current goes, your thumb points in the direction of B.
Yeah, this time.
So now point your thumb in the direction of B,
And-
your fingers wrapped in the direction of the current.
Yeah.
So how would this have to go? Point your thumb in the direction of the induced current, the red. How does fingers go? It goes like this.
Clockwise.
So how does it go? It goes like this. So the current would actually be this. This would be your induced current. This is your induced current. Okay. Now the other thing, what would this look like here? If I have a B coming out here, what does that look like?
What does what look like?
If bees are coming out here, what does that look like right now? Okay, so what does it look like? A north pole.
Oh,
That looks like a north pole here. What I would convince you of, you know, if you played with these as a kid, you know, if you take two north poles together, or two like poles, what do the magnets do?
repel.
They repel each other. I'm going to show you why that's the case. I'll show you why next week. Why that's the case. Okay. But you're going to get opposition here. So when you actually take this and move it up like this, there's actually going to be mechanical resistance on your hand. You're actually going to see this. Okay. That's Lenz's law. Now, let's say you go all the way this way here, and then you start going out to the other end.
Yep. Physically, what's happening between the magnetic fields?
What do you mean?
Like, since how are magnetic fields translating into, like, what's actually going on at a physical for there to be a resistance?
Okay.
Since
I
I understand that there's two fields, but.
Yeah. Well, what I'll do is I'm not going to show you yet. I'll show you why these two north poles here would actually repel each other. There's a reason why they do. It has to do with the fact that they're actually flowing out. Has to do with that. So right now, when you do this, you're actually going to get actual physical effects on here. Now you can actually go through and you can figure it out for another reason too. But hold on. Let's get all the way through here. I'll show you one where it's a little easier to actually like that one. Let's go all the way through.
That's your love.
Yep.
So you're saying that the loop itself would have a magnetic field now?
Exactly.
How does that work?
Lens is all fairly small. But this object right here, that loop, sees a magnetic field changing through it, and it's going to induce a current. It's going to induce an E field will go like that. That produces that current.
So moving magnet basically
Produces an electric field.
two magnetic.
Well, you have this magnetic field just from the bar magnet.
Yeah.
So that's in permanent.
Is that how you
But
make a
it
magnet?
induces-
Part, yeah.
It induces current in
In the actual loop.
yeah.
And that current in the loop is connected with this.
So basically, magnet creates two magnetic.
Well, this magnetic field here is already this is permanent.
Yeah.
Okay. What it's going to do is that this one here is produced by this student. Okay. Let's go all the way through. So now let's say it's like this. What happens in this case? How does the magnetic field look for the south pole? It comes out like this.
It's gonna attract it.
Exactly. Now, what's happening to the magnetic flux going through the loop? Is it getting stronger or weaker?
Weaker.
Yeah, so as this goes like here, the magnetic flux going in the upward direction, that's now decreasing. So in this case here, the upward flux is decreasing through the loop. Yeah. What does Lenz's law state? The current's going to be induced in such a way to oppose the change. What is the change? It's decreasing up. So this is decreasing up. What does it want to do? It want to create another B field
Increase them down.
in the same direction to bring it back up to what it was. It wants to oppose the change. Okay. The change is that it's getting weaker this way. So to oppose the change getting weaker this way, it creates another magnetic field going in the same direction to bring it back up to what it used to be.
Yeah,
So this is going to be like this. So how does that current now have to go? From the direction it goes like this. So this is now the direction of the induced current. And this end here acts like a what? The B field coming out? A north pole. What do the north and south poles do? They attract, and you'd actually have a drag on your hand going this way. Now, what happens if then the magnet goes back down through the hole? What happens?
Same thing.
The current's going to change, and then what happens if you go back up through the hole? Change. What's going to happen to the current going through here?
That's called alternating.
That's called alternating current. Okay. So if you have a loop and if you have a bar magnet going up and through it like this, you're going to get the current going like this. Okay. And that's actually how a power plant works. They basically get a whole bunch of monkeys, okay, feed them bananas, and then a whole bunch of, they have little rings like this with bar magnets, and the monkeys all day go, wah, wah, like this all day. And that's how we get power.
So
That's how the entire country is, and all the world basically is basically by hiring monkeys to do it.
That's banana.
Crazy.
Well, okay, for nuclear.
Yeah, enjoy your weekend.
For nuclear, they have to collide atoms together. Right?
Turns out, no, it's just they have monkeys again.
Yeah,
Slingshots.
monkeys. I mean, monkeys.
Monkeys are everything.
They're like charging atoms and shooting them.
Yep,
with bullets.
that's, everything works for monkeys.
Nice. Banana.
Yes. Come over. Yep, I got the wall.